My name is Jason Kennedy, and this project was created alongside doctors Blesson, Varghese, and Reaño. And we are located at the Queen's University, Belfast, in the United Kingdom. So this is a presentation for our first work using our framework called AVEC, and AVEC stands for Accelerator Virtualization in Edge Cloud Computing. The purpose of AVEC is to offload intensive accelerator workloads from an under-equipped node to a more powerful node elsewhere in the network. And the purpose with this work in particular is to investigate the feasibility of doing this with GPU accelerators using deep learning workloads. So to start off with some background, the type of network that AVEC is designed to run in is called an edge cloud network. The purpose of this type of network is to incorporate edge computing alongside cloud computing. Premise behind edge computing is to bring data computation closer to where the data is generated, and that way we can lower communication times between devices. The cloud itself is usually quite a larger geographical distance away from user devices than edge devices would be. So by using the edge, we can also reduce metrics such as bandwidth usage at the cloud. All of the end user devices in this type of network may not necessarily have access to their own accelerator. Therefore, we anticipate that they'll need to access accelerators elsewhere in the network. These networks themselves are quite heterogeneous in nature, meaning that at each level or at each node, there's various amounts of computing power available, as well as the potential for hardware and software compatibility issues, which will need to be considered. So some background on accelerators themselves. So workloads that we would execute using AVEC in this type of environment can benefit from accelerators due to the massive parallelism capabilities of accelerators. A common example of an accelerator would be a graphics processing unit or a GPU. And these are what we focus on using within AVEC. We have not incorporated other types of accelerators into AVEC as of now. By placing these accelerators at the edge, we can increase the execution time or decrease the execution time of applications. And in order to actually execute these applications on the accelerators, we need to use frameworks such as CUDA or OpenCL. Within AVEC, we use CUDA. So in order to actually execute something on a GPU, we need to use what's known as a kernel. A kernel is essentially a function or a series of routines that are stored and kept separate on the GPU. They work by the CPU will take the input from the application and send it to the GPU. The GPU then executes the kernel on that input it received, and then the GPU sends the output of that kernel back to the CPU. GPUs themselves tend to have a lot more cores than CPUs, which is what allows for this massive amount of parallelism. And then finally, some virtualization background. So virtualization of accelerators is the process of executing the kernel in a remote accelerator using the input that is taken from a local node's CPU. Virtualization allows for computationally weaker nodes to have access to more powerful resources, which allows these nodes to achieve a higher throughput. GPU virtualization in a cloud edge network can be achieved by intercepting local calls to a local GPU and forwarding them to a remote node with an accelerator. The function will then be executed on the remote node, and the output of that kernel or function will be sent back through the network to the local node, where the application can continue as usual. Within AVEC, we aim to do this in a transparent way, meaning that the virtualization process will be carried out in the background without any modifications being needed on the source code of the application. By completing this work, we aim to answer these following research questions. Firstly, how can accelerator virtualization be offered at the edge given its limited compute resources? So in order to address this question, we present AVEC as a framework that supports the use of GPU virtualization in a cloud edge network. AVEC itself is designed to be portable to aid with edge deployment, and the key advantage of this proposed framework is that we do not need to make any source code modifications and that it is compatible with any CUDA-capable GPU. Next research question is what overheads are incurred in virtualizing accelerators at the edge? So the key motivation behind addressing this question is to determine whether the computational benefits that we receive from using a virtualized remote accelerator is enough to offset the additional overheads incurred. These overheads will come from the communication latencies between the local node and the remote node, for example. We identify the areas in which these overheads occur, and we show that despite these overheads, AVEC can still achieve up to a 7.5 times speed up. And then for our last research question, can GPU accelerator virtualization at the edge improve the execution of real-world applications? So the answer to this question, we demonstrate that it is in fact feasible to offload these computationally intensive workloads using GPUs. And in our experimental evaluation, we carry it out using a deep learning application called OpenPose. OpenPose uses the Caffe machine learning library, and it takes in images or videos and makes estimations of people in the frames. So for our motivations behind AVEC, why we have designed it the way we have, our first one is computationally intensive workloads require hardware acceleration. So many different types of workloads that would be executed in this type of cloud edge network will be computationally intensive. For example, the deep learning algorithms that we focus on. In this type of environment, we believe that you can split these algorithms and execute them across different nodes in the network in order to achieve a performance gain. The next point is accelerators need to be brought to the edge. So although workloads can rely on the cloud for now, we believe that there is a performance gain from using the edge over the cloud. It's possible for both end users to offload to the edge as well as for the cloud itself to offload to the edge. And in both cases, we would see benefits such as response times of applications being minimized. Next point, multiple workloads need to share edge accelerators. So the edge environment itself is anticipated to be busy with many, many devices being connected to it, just like we see with cloud computing. Therefore, it is essential that multiple devices can share the same accelerator on a remote node. While moving these accelerators to the edge does make them more accessible, any solution doing this should be mindful and consider that these workloads need to be executed concurrently on the remote node. And then for a minimum source code, modification should be required. In an ideal solution offered at the edge, it should be less intrusive. The solution itself should be flexible enough that any existing application can be scheduled on it, and whether that is that they are located at the edge or the cloud, based on the availability and proximity to the end user. And then lastly, overhead should not offset the performance benefit. So this is a pretty obvious one in that whenever we provide a remote accelerator virtualization, we need to make sure that the performance gain is able to overcome the overheads incurred. And we can do this through implementing optimization such as efficient data transfer or execution strategies. So on to discussing our approach or how we implemented AVEC's functionality. So with AVEC, we aim, of course, to provide remote GPU acceleration for deep learning libraries. And the first deep learning library we used was called Caffe. Caffe itself is an open source library for deep learning algorithms. And it makes use of CUDA in order to execute its kernels on the GPU. With AVEC, we've designed it to work as a middleware that intercepts calls made to the Caffe library and forwards it to its own library, so that the input of these functions required by the Caffe library can be forwarded to the remote accelerator. And this is a technique known as API interception. Our use of API interception is transparent. So again, that means it's done in the background and we don't need to modify the application that's being run in any way. So in terms of the architecture with AVEC, so when a connection is established between the local node and the remote node with the remote accelerator, we can model that as a client-server relationship. The local node, of course, being the client and the remote node being the server. So in order to move a kernel from the local node and execute it in the remote node, AVEC firstly needs to extract the required input data to the function from the application. That data is then packaged into the communications module, which establishes a link or a connection between the local and the remote nodes using, for now, a TCP connection. The interception library is stored on the local node and contains the overridden functions needed to forward the input for the deep learning library. Once the server instance of AVEC receives the required data, the actual corresponding kernel in the deep learning library is executed in the remote node using the remote GPU. And then the output of this kernel is sent back through the communications channel to the local node. And using this output, the application can continue its normal execution. So in order to test AVEC, we have used a lab-based setup which we use to mimic a cloud edge network, comprising of 3 parts. So firstly, for our user device, we have a Jetson Nano. At our edge level, we have a Jetson TX2. And then for our cloud, we're using a desktop PEC, which has a RTX 2060 GPU in it. The table at the top right shows some basic statistics about these devices. Key thing to take away is that the edge node is roughly twice as powerful as the user device, whereas the cloud is substantially more powerful. Within each test, the Jetson Nano or our user device will offload the kernels of the application to one of the devices, either at the edge or the cloud. And the tests are carried out using a sample application called OpenPose. OpenPose is an application that takes in either video or images as its input, and then detects if there's any people in the media, and if there is people, it draws a predicted pose using a deep learning library called CAFE. So in order to test, we used a short sample video and varying batch sizes of images from a data set. And we use 2 test scenarios. We have the edge scenario, in which the Nano offloads to the TX2. And our cloud scenario is when the Nano offloads to the RTX GPU. So in terms of our results from our image tests, so we use batches of 64, 128, and 256 images, and these all have varying resolutions or sizes. Initially, the tests were carried out on the OpenPose application on each device without using AVEC, and that table in the top left shows that native execution as our baseline. So from the table, we can see it takes roughly twice as long on each device whenever we double the amount of data, which is what we would expect. We then took these same images and we did the test again, but this time we incorporated AVEC. So firstly with our user to edge offloading, and then with user to cloud offloading. So the graph in the bottom left shows these results. So the first sets of columns represent the native application execution without using AVEC. So it's just being run on the Jetson Nano. Device to edge then represents using AVEC to offload the kernels to the edge device, and then device to cloud shows again offloading to the cloud device. And then within each section we have the 64, 128, and 256 test sizes. So in this graph we can see that the execution time falls when we offload to the edge, and then falls even more when we use the cloud. And this is what we would expect to see, as the cloud has a much more powerful accelerator. So in terms of our video results, so the video we used was a 204 frame clip, and a key difference is that OpenPose does not save the output of a video test like it would with images. So this first graph shows the offloading using the video. And again, we see a similar trend that we see with the images, where we get a speed up when we offload to the edge, but we get a much greater speed up when we offload to the cloud. And then the last table in the bottom left shows the relative speed up we achieve using AVEC in comparison to the native execution using just the Jetson Nano or our user device. As we can see, the edge has a relative consistent amount of speed up from 1.32 times to 1.45 times speed up across all the test types. And the cloud has a greater speed up, but a similar amount of consistency between the image tests, where it's all around 3 times speed up. But whenever we bring the video to the cloud offloading, we get a much greater increase, which is up to 7.5 times speed up. So to discover why we got the results that we got, we began a process of profiling the overheads. So firstly, when we compare the number of kernels executed natively with and without AVEC, we go from 27 unique kernels to 13 kernels. And similarly, when we look at the number of kernels executed on the virtual accelerator, we have 17 being used. So these additional kernels, other than the primary kernel that is responsible for the actual deep learning algorithm, are support kernels, which are used for memory transfer between CPU and GPU or resizing the data. So these four graphs show a more detailed breakdown of where the time is being sent when we use AVEC. For the individual bars, so firstly GPU, which represents the amount of time spent in the GPU executing kernels. Comms represents the amount of time spending data back and forth and preparing that data to be sent back and forth. And then other represents all the other time spent, which is primarily with OpenPose specific functions or with idle times. So across the different tests, we can see that the communications time differ between the devices, despite the fact that we use the same type of connection, which is a wired Ethernet connection, and we're sending the same amount of data back and forth depending on the image test type. Another point to be made is that the amount of time spent in other is a lot higher for the cloud than it is with the edge. Reason for that is the cloud is spending a lot more time idle waiting for the user device with a nano to catch up, since the cloud is so much more powerful than the nano. The amount of time spent in the GPU is what we would expect. The GPU time for the cloud is a lot shorter than it is for the edge, and that's because a more powerful GPU will execute faster. So some key points that can be taken or observed from the experiments we've conducted. Firstly, more powerful accelerators outweigh additional overheads. This is evident because we're able to get a speed up in either device that we offload to. Execution times depend on the hardware. So when we say the hardware, we don't just mean the accelerator. This is because of the differing communications times across the devices. There's an upper limit on speed up a virtualized accelerator can offer. So again, from the overheads, we see that the cloud has a high other time, which is due to it being idle, waiting for the user device to catch up. And then lastly, video performs better than images due to local load limitations. This is because the images are saved as output, whereas the video is not, so therefore the video is faster. So in terms of our current limitations and where we plan to go in the future with this, firstly, we only consider one deep learning library, which is the Caffe deep learning library. And in the future, we want to incorporate other types of deep learning libraries. So no mechanism that migrates workloads between accelerators. So due to the dynamic nature of cloud edge computing, AVEC must be capable of moving workloads to alternative nodes based on the workload or user's requirements. This can be achieved through containerization that can package instances of AVEC into a separate virtual space, which allows for isolation. With containerization, we'll also be able to overcome some of the difficulties presented by the heterogeneous nature of cloud edge computing. Containers also allow for an easy avenue into achieving migration, as this entire instance of AVEC that's packaged into a container, we can simply move that entire container between nodes. Migration itself also improves aspects such as the reliability of AVEC, as we have higher fault tolerance. And the last limiting point is lack of device-aware scheduling. So again, with the heterogeneous nature of cloud edge computing, AVEC needs to be aware of what type of hardware or what the limitations are of each node within the network. We need to look at metrics like accelerator usage or latency or power usage, for example. We need to take all of these factors into consideration. We need to come up with a scheduling system. We can then use that scheduling system to send a workload to the best possible node to get the best results. So finally, for our conclusions, so firstly, we presented AVEC, which is our framework for GPU virtualization in a cloud edge environment, and we use API interception to achieve that. We tested and showed you the results of using AVEC with our real-world application OpenPose. We went on to identify the areas in which the overheads are occurred, and we discussed the overheads. And then we showed that despite these overheads, we can still achieve a performance increase, which was up to 7.5 times with the video. And finally, we identified our limitations of our current prototype, and we picked some future goals that we want to try and achieve. So thank you very much.